Continuing the discussion regarding 802.16.1, and we started talking about the physical layer characteristics, and we said that because this standard talks about point-to-point communication with line of sight, so direction of the communication is very important in that case, and that's why we don't need to have sub-channels, so the whole spectrum is actually one unit. Hence, there is one single carrier for one wide range of frequency, so the whole spectrum is actually used as one channel, and the bandwidth of this can get up to 28 megahertz, which allows for data transmission up to, as we said last time, around 134 megabits per second. So in the physical layer, we can use bidirectional communication using one of these two techniques, either FDD or frequency division duplexing or time division duplexing. This is a little bit different from TDMA and FDMA, right? So this is used for bidirectional communication. So if we have TDD, this means that we have a time slot for one direction and another time slot for the other direction. So in that case, the frame, as we will see in a minute, the frame is actually divided in the time domain into one part, which is used to send, and another part is used for reception. Whereas for FDD, you have two frames that concurrently go in time together, and one is used for transmission and the other is used for reception, and that's what we call full duplex or half duplex. For the case of TDD, it's half duplex, so we send and then on another time slot we receive. Versus FDD facilitates the full duplex where we send and receive at the same time. So this is how it looks like. So the frame, this is for TDD. The frame is actually subdivided into one downlink and one uplink. By downlink, we always mean the communication from the central station or from the coordinator or from the access point to the node. Whereas for uplink, we always mean from the node to the central station. Okay, so this is like a common terminology. So the word adaptive here indicates that the duration of the subframe for downlink and uplink can change in terms of size. Okay, so it can change in terms of size, for example, to provide quality of service or to provide some asymmetric type communication, in which case, like ADSL at home, that we used to use at home, it provides asymmetric type of communication where the download part is more than the upload, which follows the common paradigm of clients that usually download more frequent than working as a server, in which case they upload, right? So by controlling the size of the downlink frame or the uplink frame, we can provide either symmetric communication if they are the same, or asymmetric communication, which is geared towards either giving more throughput or more data rates for upload or more data rates for download. Okay? And then these frames are then these two subframes for TDD. Both of them, they are repeated in time to provide one frame, and then this frame is repeated in time. So each of these frames is actually subdivided into downlink and uplink. For the case of FDD, they go concurrently, so they go at the same time. So the downlink and the uplink, they use different frequencies, in which case they can go in time concurrently. So you have one frame for downlink and one frame for uplink, and they are parallel to each other in terms of time because they use different frequencies, right? So there's no advantage for one versus the other, because for TDD, there is an issue with synchronization versus for FDD, there is a complexity issue when it comes to the fact that the transceiver needs to provide communication on two different frequencies at the same time, which means that the hardware is more complicated. Whereas for TDD, you can use the same hardware for transmission and reception, except that you have to synchronize carefully the time slot used for upload and the time slot used for download, and you have to synchronize this very carefully, right? So each one has an advantage and disadvantage. One very important feature for the physical layer for 802.16.1 is what we call adaptive data burst profile. And that talks about the fact that you can actually use different modulation schemes. I'm not sure if any of you is familiar with QPSK or QAM or something like this. Maybe you have studied it in other courses. Basically, these techniques talk about the fact that we convert the bits, the encoded bits, into signals, right? So PSK, for example, talks about the fact that we map the different pattern of bits into signals, into an analog signal with different phase. Okay, so for quadrature phase shift keying, this is quadrature phase shift keying. It talks quadrature here refers to 4, which means that we have 4 distinct and different phases for the same signal. So the same signal, we shift it, with a phase shift, 4 different phases to represent 4 different combination of bits, which means that using 2 bits, you have 4 different combinations. You have 0, 0, 0, 1, 1, 0, 1, 1. Okay, each of these will have different phase in time to represent these bit combination into an analog signal, right? So 16 QAM, for example, this is quadrature amplitude modulation. So this actually uses both the phase and the amplitude, because we have the amplitude modulation, which uses the amplitude of the signal to represent the different bit combination. So for example, 0, 0 uses a certain amplitude, 0, 1 uses a different amplitude, and so on. Okay? So you have amplitude modulation and you have phase modulation. So QAM here talks about the fact that we can combine the two. So if we were to draw what we call the amplitude phase diagram, so this is the phase and this is the amplitude. So we can represent the bit pattern using one point in this two-dimensional plane. So this, for example, this point, for example, indicates 0, 0, 0, 0, something like that. Okay? So we can represent different bit combinations using one point on this plane to indicate that for this we use this particular phase shift and this particular amplitude to represent the specific bit pattern. Okay? And 16 QAM here talks about the fact that we can have 16 different amplitudes and phase, which means that we can represent up to how many bits? Yeah, 2 to the power n is 16, which means that n is 4. So we can have 4 bits, okay? These 4 bits, they need 16 different phase and amplitude in this phase amplitude diagram, okay? So why do we need to use different types of modulation, and what is the benefit of this? Well, as you can see here in this diagram, the closer these points are, the prone the communication will become, in terms of if you have any noise in this point, this point can easily be shifted here, okay, at the receiver side, because at the receiver side, when you go through the channel, you encounter some noise. So when you encounter this noise, the noise might affect the phase and or the amplitude, right? Which means that at the receiver side, this point might be shifted a little bit, right? So it might actually be interpreted at the receiver side as this point rather than this point, which means that this will lead to an error. And the closer these points are in this domain, the more likely or the more probability that we will have some errors caused by the noise on the channel. That's why the higher the modulation, or we call it sometimes the modulation level, or sometimes we refer to it as the constellation. So the higher this constellation, the more prone or the more probability of errors. Okay? So we have to be careful that when we increase the modulation level, we increase the probability of error. So does that benefit us in any way? Yes, because of course, with this modulation, I can represent more bits, which means that I can send more data in the same spectrum or in the same frequency range, right? So the capacity of the system becomes more, right? So the higher the modulation level, the more the capacity of the system, but we increase the probability of error. So there is a trade-off, okay? So there is a trade-off. And it would be nice if we can sort of estimate or sense if the channel is good, okay, which means that the noise level is low. This will allow me to increase the modulation, okay, which means I will have more throughput. And because the channel is good, the probability of error will be low anyway, so these points will not move back and forth and create more errors. Okay? So if the channel is good, increase the modulation, because this will allow you to increase the throughput. If the channel is bad, okay, then you have to lower this modulation level, which will force you to lose some throughput. But I have to do this in order to maintain the probability of error within certain level. Because if I don't do that, I will end up with high probability of error. So I will send data, and the data will become, will become incorrectly decoded at the receiver side, which means that the transmitter will have to retransmit. So we'll have to repeat the job several times. So that's not good. So that's why, if we use this adaptive data burst profiles, this will allow us per frame, okay? So at each frame, the physical layer is allowed to change not only the modulation level, but also the forward error correction scheme. Because the same thing, the forward error correction scheme is actually kind of correlated to the modulation. Why? Because the forward error correction, remember we talked about the forward error correction 455, so I can have more bits to be sent with the data. So if the data itself has some error bits, I can correct this using FEC codes, right? So I can do some error correction without having to go back to the sender and ask the sender to retransmit, right? So, and as we said now, if we increase the modulation, we will have higher probability of error, which means that if I raise or if I increase the size of the FEC codes, this will allow me to compensate for the errors that might happen. Okay, so both of them are correlated, and that's why the physical layer uses some adaptive technique to adjust both the modulation and the forward error correction codes to estimate at every frame what is the best modulation level and what is the best FEC size of the codes, so that I can get the best performance or the best trade-off between capacity and the probability of error. Okay, so that's a trade-off that's used in the physical layer in this standard, and of course that's one thing that I can use for quality of service. So I can provide some service differentiation using this. So by changing the modulation at every frame, and remember, every frame is assigned to a particular user. All right. So for a particular user, I can increase the modulation level, which means that I give this user more throughput. Okay? But I have to do this taking into consideration two things: the throughput and the probability of error. Okay? So if the traffic coming from the user is actually loss tolerant, so I can comfortably increase the modulation, because even if there is some packet loss, there's no problem, because the traffic is already tolerant to the packet loss. All right, so I can use this notion or this idea for service differentiation. Okay, so that's very important. So of course, what type of modulation and what type of FEC that's used in every single frame is defined by what we call interval usage code. So the code will inform the receiver, okay, what is the modulation level and what is the FEC size that's used for a particular frame, so that the receiver can actually, and of course this comes before the frame, so the receiver can use this IUC or interval usage code to be able to decode all the incoming frames. Okay? And there is downlink interval usage code or uplink interval usage code. Okay? Okay? So very quickly, in the physical layer, we use two different time division multiplexing. So there is the time division multiplexing and the time division multiple access. What is the difference between the two? Well, when we say multiple access, we are talking about multiple nodes trying to have access to the medium. Okay? Whenever you don't see the term multiple access, this means that you don't necessarily have multiple nodes trying to access the medium, which is the case for TDM. By TDM here, we refer to the transmission from the central nodes, from the central base station, to the other nodes. Okay? So time division multiplexing is one-to-many. And because you always have the communication starting from the central node, okay, so the communication is initiated from the same node and uses one single clock for transmission. So if I'm talking about one time slot to send to node 1 and one time slot to send to node 2 and one time slot, so who controls the start and the end of each time slot? It's the central station. So in that case, I'm using the same clock for transmission. So I can perform the synchronization easily. So there is no problem with that. And that's why you see here for TDM, the frames are continuous and they are tied to each other and they are right next to each other. So there is no gap. For TDMA, we're talking about uplink. For the uplink, you have different nodes initiating the communication to the central nodes. So each node has its own clock, right? So when you have multiple nodes, each node has its own clock. So that's why we need to have this gap between the time slots. Why? Because each node will have to rely on its own clock to recognize the beginning of the time slot. So if there is any clock drift between the nodes, okay, the time slots will overlap. So that's why you need to have like some guard space to account for the clock drift between the nodes. So that's why TDM is different from TDMA. So TDM is used for downlink transmission and TDMA is used for uplink transmission. Okay, مفهوم الحتة دي؟ Okay, so we'll start.